believe in the future, wires will unite different cities, and a man in one part of the country may communicate with another by word of mouth in a distant place.
Central? Central, will you connect me to 1-5? Do you hear me? Jimmy, is that you? Hey, talk up.
Oh, my darling, last night was so wonderful.
2 men to mend the awning.
She said that. Well, I gave her a piece of my mind. And then you know what...
This old switchboard could talk. Wow. Your ears would sizzle.
Young man, you brought my daughter home after dark. And I don't believe that poppycock about the horse going late.
1880. We take Alexander Graham Bell's invention for granted today. Perhaps we should. But isn't it incredible that millions and millions of people can talk simultaneously to practically any spot on Earth? In the beginning, back in the old days, the telephone was something of an oddity, to say the least. You'd pick up this receiver to see that the line was clear. Then you'd hang up, ring with this ring. And you'd pick it up again and tell the operator what number you wanted.
Central.
6A, please.
Thank you.
She'd hook it up for you on her switchboard. If there was anybody home, they'd answer and you could talk. Sometimes. The word telephone means far sound, you know. Calling next door could be long distance. The problem, you see, was transmission. The farther you were from the other party, the weaker your voice came through, and vice versa. The telephone converts your voice from sound waves into electrical waves, and back into sound waves. In those days, that was quite a trick. But once the voice went out over the wires, it lost all of its zip. And as we said, the farther it went, the weaker it got. Without a way to boost the signal, even calling across town meant some shouting. It took, however, some brilliant work by Bell Laboratories scientists and engineers to solve that basic far sound transmission problem. And here's how they did it. The vacuum tube. Invented by Dr. Lee DeForest and improved by Bell Laboratories, it literally revolutionized communications. Its job, to amplify, boost the voice signal. Relay stations set up along the way used vacuum tubes to keep the voice signal loud and clear as it raced on toward its destination, drawing the far sound nearer. Yet when wires are loaded with a lot of conversations that are boosted in strength and travel some distance, something else happens. Let me show you. You see, instead of sounding like this, 1, 2, 3, 4, 5, your voice comes out sounding like this. 1,
2, 3, 4, 5, distorted.
This gentleman, Harold Black, solved the distortion dilemma. What an inspiration in devising this circuitry. Black created what he called a negative feedback amplifier. What it did was take a little bit of the distorted signal, reversed it, just like a mirror, put it back into the circuit, and run it through again, canceling out the distortion. With negative feedback, telephone transmission became literally, pardon the pun, clear as a bell. In the meantime, of course, the laboratories came up with a host of other remarkable developments. One invention, for example, electrical recording. Another, work that helped give sound to the movies. Along with the contribution to radio broadcasting also came developments in shortwave. And soon they had people talking ship to shore.
Reception good. Reception good. We're approximately 1,700 miles from Boston. Position 48 degrees, 15 minutes north.
Air to ground.
Hello, ground. Hello, ground. We're over Elmira at 5,000 feet. We hear you. We hear you, ground.
Even continent to continent.
Hello, New York. New York, this is London. Hello, New York. This is London. I hear you now. Yes, loud and clear.
It was Bell Laboratories who created ways of sending television signals over telephone wires, and later through the air. Soon those cross arms and open wires stretching across the land began to vanish. Cables got better too, and bigger. Ingeniously, cables were developed you could bury, with technology allowing many calls to be carried over each single wire within the cable simultaneously. Other cables were fashioned to lie on the bottom of the sea, to function 20 years and longer, trouble-free. Plus a type of cable that didn't look much like a cable at all, called coaxial cable. Coax for short. Besides carrying more telephone calls than several cables combined, coax was, and still is, perfect for carrying television. You've probably seen these on a tower, sitting on a hill somewhere along a road. They're microwave antennas. Microwave got its start back in the 1930s at, you guessed it, Bell Laboratories, where scientists were exploring the use of radio for telephone circuits. World War II erupted, temporarily halting full-scale work on microwave, but it did offer many laboratory scientists and engineers the chance to apply what they'd learned about microwave to a host of military communications needs, including radar. With the war over, research accelerated, and soon microwave techniques and equipment had become part of day-to-day telephone and television transmission. With microwave, calls ride a radio beam from tower to tower instead of going through cables. A single beam carries some 2,000 calls at a time. The far sound has come a long way since the old days, hasn't it? But transmission progress is only part of the story. From the beginning, another vital element, switching, faced just as many challenges. If Bell System research had not met these challenges, there frankly would not be a nationwide telephone system today. You see, as soon as you have a number of phones, you must be able to connect the right two. Without switching, wires would have to connect every phone directly to every other phone. And even that wouldn't work very well. In the beginning, all switching was done by hand at a switchboard, by Central. Old-timers remember her. Central was just the ticket. She could do everything you needed. Remember numbers, pick them out on the board, plug them in, ring, unplug after the call. But unfortunately, Central went the way of the horse and the buggy. The demand for more and faster service simply overwhelmed her. In fact, were Central's method of switching still in existence, every person in the United States would have to be a telephone operator to handle today's volume of calls. The problem was solved with two of the world's great technological innovations, automatic switching and the dial telephone. With both, one telephone could find another, without an operator, without even a switchboard, if the proper number was known. By the time direct distance dialing went into service, the cost of a coast-to-coast call had fallen from $22 to less than $2. Alexander Graham Bell used to say, "Get off the road, explore," as though he knew where the keys to progress lay. You can't invent, create, or make things new unless you believe in progress and change. If there's such a thing as tradition in the Bell system, it's the tradition of finding new and better ways, as more than 17,000 Bell patents in just about every field of scientific endeavor testify. Here's an example. The transistor. Like so many inventions, its mother was necessity. Its father, ingenuity, the type that has made Bell Laboratories one of the most renowned research and development organizations in the world. The basic need came from the growth of the telephone network itself. Each day, hundreds of millions of voices and images move through the network. Each one is switched again and again, and boosted in strength again and again. If you can save a fraction of a second during switching, that adds up. The hope was to invent something that could do the same things that vacuum tubes do, switch and amplify, but do them better and faster, and occupy less space. Now, that was a tall order. Scientists at Bell Laboratories began by experimenting with various materials to learn more about how electrical current moves. This is silicon, more pure than even nature makes it. Pure silicon doesn't carry electrical current well. But when you add certain kinds of impurities, such as boron or arsenic, very interesting things happen. And what happens is the phenomenon that led to the invention of the transistor by the laboratories in 1947. The transistor amplifies or boosts in strength an electrical signal. Here's how it does it. It accepts a weak incoming signal, then recreates the same signal, but increased in strength many, many times. There are several types of transistors. This one has three parts: an emitter, a base, and a collector. The incoming signal passes first into the emitter side, then into the base, which is a sort of valve that controls the strength of the signal when it passes into the collector side. Two sources of power are involved in this process. A small battery, through whose circuit the incoming signal is fed, and a large battery, which pushes the signal on its way. Let's look a little deeper. A transistor is made from a slice of pure silicon. To allow electrical current to flow through the silicon, tiny amounts of arsenic atoms are added to the emitter side and to the collector side. The atoms give these sides extra electrons, which are negative charges. A few atoms of boron are added to the base. Boron provides extra holes, which are positive charges. It is the interaction of these negative and positive charges that helps make the transistor work. But the negative electrons can move only when an electrical current is introduced into the transistor. Watch. The negative electrons in the emitter side are attracted into the base because the small battery makes the base more positive. Positive attracts negative. From here, the electrons flow into the collector side, driven by the large battery. Let's see what happens when only the large battery is working. The electrons are pulled away from the base by the voltage of the large battery, leaving only positive charged holes. Thus, no current flows. But when the smaller battery is connected, the negative electrons are injected from the emitter into the base, and from here respond to the power of the large battery. So the current which flows is controlled by the small battery and has the power of the large battery. Now let's connect a weak telephone signal to the emitter side. Variations in the telephone signal control the flow of electrons through the valve-like base into the collector side of the transistor. Now the signal current is pushed by the large battery, so it is much stronger than before, as much as 1,000 times stronger. In other words, the signal is amplified and the transistor is doing what a vacuum tube does. But it's far smaller. It works much faster, doesn't heat up, doesn't take much electricity. Incredible, huh? A transistor just sits there and, well, transists. The one under this microscope is hooked up, so you can hear it amplify. There it is, a transistor. This one even smaller than a grain of sand. A miracle of modern technology. A signal is being sent into it. The oscilloscope screen displays the signal. Now, amplification on, off. The transistor has indeed had a profound influence on the world we live in. They're everywhere, in portable radios, television sets, hi-fis, hearing aids. The artificial larynx, which enables those who have lost their vocal cords to speak.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Roger, we got a roll from
Tower cleared.
Roger, roll.
The entire space program, the entire computer industry, both became possible only through the transistor and what began as a search for better telephone service. But all that was yesterday. Here's today. Look closely. There in the center, about the size of a pinhead. Engineers call it an integrated circuit. It contains hundreds of these transistors and other components, micro-miniaturized, invisible to the naked eye. The impact upon communication of such solid-state developments as the transistor and integrated circuits has been tremendous, and it's just beginning. Look what's already here. An all-electronic telephone office, superior in every way to anything before it, that operates in millionths of a second. It can diagnose and automatically correct its own malfunction. One that performs 1,800 basic jobs in the time it takes a person to blink his eye. That offers customers a bundle of new telephone services like call waiting and call forwarding. If you're on the phone while someone else tries to call you, call waiting lets you know it, so you can hold your first call while answering the second. Call forwarding is a new service that lets you leave the house and have all your incoming calls transferred to wherever you plan to be. Here's another. This is a traffic service position system. It's being installed in telephone offices across the country. With it, operators can handle far greater numbers of calls and help customers faster than ever before. It takes a fantastic amount of know-how to design, build, install, and man communications equipment such as this. That's where Western Electric and the telephone companies come in. Western Electric's job is to translate inventions into the real thing. The central office equipment, the cables, the new models of telephones that people use. It's a big job. The final inspection station is a long way from the laboratory. Materials are purified down to the last atom. Mother Nature herself is seldom so careful. Even when the material is right, someone must be able to work with it and do everything exactly the same every time. Dissolve away a layer only a few atoms thick. Make a cut within a 1/2 of an inch. Weld connections finer than human hair. Precision, 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 multiplied 1,000,000 times. Whether the end product is a telephone, cable, or an entire electronic central office, a Western Electric plant is not the place to look for yesterday. Yesterday. We used to call it tomorrow, remember? In yesterday's tomorrow, communication satellites were to shrink the world. And this one did just that. Telstar. This is only a model. The research and development of Telstar by the Bell System gave birth to the entire era of worldwide telephone, television, and data transmission via space. Every kind of progress has a beginning, a starting point. And then someone has to move ahead and take the step that might make tomorrow better. Take this circular waveguide. A waveguide no wider than a man's wrist that can carry 250,000 voices at a time. One day, one tomorrow, waveguides may join coaxial cables on high-capacity routes. Another tomorrow being perfected by Bell Labs, the laser. A remarkable invention that produces a remarkable light. In theory, a single laser beam could carry all the telephone conversations and television pictures going on right now around the world. Think of it. Some tomorrow. And how about these recent developments for telephone systems? An emergency storage battery with a lifespan of more than 30 years. Tiny indicator lamps that will burn continuously for 10 years. The world's first tubeless color television camera, which weighs less than 10 pounds. Remember the story called Through the Looking Glass? Sure you do. As Alice's Adventures in Wonderland. She looked where everyone else had looked and saw something no one had ever seen. That's what happened with fiber optics. Well, people have been making cloth from glass thread for years. And everyone knows that light goes through glass. Now, suppose you took a bundle of glass fibers made into a flexible pipe, like this one, which can bend around corners, and sent a laser beam loaded with telephone calls through it from one city to another. Wouldn't that make some telephone cable? Scientists are trying to do just that. If no one tries, no one will find out whether it's practical to use glass fibers to carry millions of telephone calls. With the kinds of advances in transmission that we've been seeing, you can bet that switching research is getting a lot of attention too. Integrated circuits, tiny and wondrous as they are, would be hard put to handle millions of calls traveling down a laser beam at the same time. Several exciting areas are being explored. One involves magnetic bubbles. Everyone has known about magnetism for a long time. Not long ago, scientists found out something new about the subject. In some materials, a tiny bubble-shaped magnetic field can be formed and controlled. The field can be moved back and forth, up and down. Used to open and close a circuit, magnetic bubbles make a switch smaller than anyone dreamed of years ago. Oh, what an exciting world. Satellites, waveguides, lasers, magnetic bubbles, fiber optics, picture phones someday, maybe even in color. In 1878, only 2 years after he invented the telephone, Alexander Graham Bell did predict that men in distant places would one day communicate. But could he have ever imagined that one day they'd see each other by phone? Who knows? With his incredible foresight, maybe he did. I, for one, am sure he did.